Hello, my rubber hearts. Welcome back to season 3 of My Rubber Heart. In our last episode, we explored the invisible network inside rubber through swelling tests, and we learned how those tiny crosslinks tell us about strength and flexibility. Today, we are moving from structure to time. We are talking about aging and durability, how we simulate years of service in just few days in the lab. Rubber doesn't fail suddenly. It ages. Slowly, quietly, the network you built in the cure starts to change. Heat, oxygen, ozone, and sunlight attack it in different ways. And in the lab, we have 3 main tools to study that process: air oven aging, ozone testing, and UV weathering testing. Let's start with air oven aging because it's the foundation of all durability testing. You take your vulcanized samples, usually tensile dumbbells and harness buttons, all from the same compound batch, and first measure their properties: tensile strength, elongation, hardness, maybe compression set. Those are your baseline numbers. Then you place them in the air oven, where controlled temperature and airflow accelerate the natural oxidation process. The critical thing here is how you set up your samples. Each piece must be freely exposed on all sides so hot air can circulate evenly. If samples touch each other or rest flat on a tray, you'll create spots that age slower because oxygen cannot reach them properly. So how do we do it right? Most labs use perforated stainless steel trays or aluminum racks with small hooks made of wire or thin metal rods. The dumbbells are usually hung vertically by one end, using those hooks spaced so they don't swing into each other when the air circulates. For small plates or buttons, technicians use wire grids or fine mesh stands so the air flows under and over. Some labs even use glass rods supported across the shelf with thin wire loops holding each specimen. The key idea is that the sample should float in the airstream, not lie flat. Once the setup is ready, you choose the temperature and duration. It really depends on the application. Maybe 70 degrees for a week or 100 degrees Celsius for 3 days. If you want to accelerate the chemistry but not change it. If you go too hot, you might trigger degradation reactions that never happen in service. After aging, you take the samples out, cool them at room temperature, and immediately remeasure the same properties you measured before. The change tells you the story. A small hardness increase and a 10 to 20% drop in elongation are normal, but big changes, say over 30% loss in elongation or tensile, show that oxidation is really breaking chains and tightening the network. That is why most standards like ISO 188 or ASTM D573 use a 30% deviation limit to decide if a compound passes or fails. It's not random. It's based on where visible brittleness usually begins. Now, heat and oxygen are one kind of enemy, but they're not the only ones. Let's talk about ozone. Ozone is sneaky. It attacks rubber that have double bonds in their chains: natural rubber, SBR, NBR, and CR. And it causes those distinctive, fine cracks that grow perpendicular to the direction of stretch. In the ozone test, you stretch samples to a fixed elongation, usually 20 to 30%, and expose them to control ozone in a chamber at about 40 degrees Celsius. Here again, setup matters. The samples must be under uniform tension, so technicians mount them on small jigs or stretch frames, basically metal hooks or rings that hold the strain constant. You leave them in the ozone chamber for a set time, often 48 or 96 hours, then inspect for cracks under magnification. The pattern of the cracks tells you a lot. Ozone cracks always run across the direction of strain because that's where the polymer backbone is opened and exposed. This test is perfect for predicting weathering and outdoor behavior. Things like tire sidewalls, rubber bands, or electrical insulators near ozone-generating equipment. Then there's UV weathering testing, which mimics sunlight and outdoor exposure. Here the degradation comes from ultraviolet radiation, breaking polymer bonds directly. The test chambers use fluorescent UV lamps or xenon arc lamps, often with humidity and temperature cycling to mimic day, night, rain, or dry conditions. After hundreds of hours, you inspect the surface chalking, discoloration, cracks, or property loss. If ozone makes cracks, UV makes dust, a faded, powdery surface as the polymer degrades and fillers or pigments migrate to the top. Now, each of these aging methods simulates a different mechanism, which is why their failures look so different. Air oven aging causes oxidation. Long chains break, the network becomes tighter, and the rubber gets harder and less elastic. Ozone causes surface cracking along the stress direction. UV causes chalking and fading as surface chemistry breaks down and loses gloss. Once you learn to recognize these signatures, you can tell at a glance what kind of aging a rubber has suffered, even without a microscope. And of course, all these tests would be disasters without additives, the real backbone of rubber durability. Antioxidants defend against heat and oxygen. They trap free radicals before they attack the polymer chain. There are two main families: amine antioxidants, which are powerful but cause discoloration, and phenolic antioxidants, which are cleaner but less active at high temperatures. Black rubbers like tires and seals often use amines because color doesn't matter, while light-colored compounds rely on phenolics. Antiozonants protect against ozone, and most of them are PPD derivatives. These slowly migrate to the surface, forming a protective film that reacts with ozone before it reaches the polymer. If you've ever noticed that brownish or purplish haze on a fresh tire, that's your antiozonant hard at work, taking the damage so your rubber doesn't. Then we have waxes, which migrate to the surface over time and form a thin physical barrier against ozone and UV. It's like a self-healing sunscreen, but it only works when the part is static. If the surface flexes constantly, like on a sidewall, the wax film breaks faster than it can regenerate. So the compound needs both wax and chemical antiozonants. And finally, pigments and fillers contribute too. Carbon black is an outstanding UV stabilizer. It absorbs ultraviolet radiation and converts it into harmless heat, which is why black rubbers survive outdoor best. White compounds use titanium dioxide for a similar effect, scattering UV light away from the surface. Colored compounds can add UV absorbers or HALS to help protect both the polymer and the pigment. When you put all of this together, the oven test, the ozone chambers, the UV weathering, and the right stabilizers, you get a complete picture of how your rubber will age. The tests don't just tell you if your compound passes or fails. They show you how it will fail, how fast, and under what conditions. That knowledge is what lets you improve the formulation and make the next version last longer. So remember, aging tests aren't about punishment, they are about prediction. They are time machines that let us see what our rubber will look like after years in the field without waiting years to find out. That's today's Toolbox episode, my rubber hearts. In the next episode, we are going to take this one step further and talk about the science behind accelerated testing, the Arrhenius equation, and how you can use it to translate your lab aging times and cure data into real-life performance predictions. Stay tuned for that one. Until next time, stay elastic and stay curious.